Now let's start to look at the computational details for the Solow model. The first computational detail we want to look at is that we argue that when we are solving the Solow model, we want to focus on the per capita variable. The reason why we want to focus on the per capita variable is because we care more about the welfare of the nation. Therefore, we prefer to look at the per capita output and all other variables such that we will be able to simplify our analysis when we express all the variables in terms of per capita. So how to do that? To begin with, we want to convert all the variables into per capita. The variables under the Solow model includes the Y, C, I, and K. Each represents the output, consumption, investment, and capital stock respectively. And these are the aggregated variables. Then we can define the per capita variable in lowercase, that is lowercase y, lowercase c, lowercase I, and lowercase k. Each represents the output per capita, consumption per capita, investment per capita, and capital per capita. And this variable is the aggregated variable divided by the size of the population. So in here we can define the lowercase y, which is the output per capita, equal to the aggregated output divided by the size of population. Then it becomes the per capita output. Same thing for consumption, for investment, and for capital. We convert all of them into the per capita variables. So then what we want to do is that we want to convert the system of equation we set up earlier from the aggregated variable to the per capita variables. And the system equation that we want to look at is these four equations. So to begin with, we have the first equation, that is the total consumption equal to a portion of the income. So how to convert the first equation that expressed in the aggregated variable into the equation that expressed in the per capita variable while holding this relationship? Well, we know that if we want to convert the aggregated consumption into the per capita consumption, then we need to divide it by the size of population. When we want to convert the aggregated output into the per capita output, we also need to divide it by the size of the population. So then we say, if we divide both sides of the equation by the size of the population, and then we will be able to successfully convert the first equation into the equation that expressed in terms of per capita variable, that is the lowercase consumption, which is the consumption per capita, equal to a portion of the output per capita, keeping the original equation hold. So how about for the second equation, that is the production function? We say eventually we will be able to convert this equation by dividing both sides of the equation by the population size, and then we will be able to express this production function into the new equation, that is the output per capita equal to the production efficiency multiplied by the capital per capita power to theta. And why we can come up with this new equation? Well, if we divide both sides of the equation by the n, and then we know that the left-hand side, the yt over nt, is the aggregated output divided by the population size, and it becomes the per capita output. That on the right-hand side, we have the denominator and n. Then we can separate into n to the power of theta and n to the power of 1 minus theta. And then the n to the power of theta can go together with the kt to the power of theta, and then becomes the lowercase k to the power of theta. So then we successfully converted to the lowercase k for the capital stock. So then we can look at the right-hand side of equation, say, hey, then why the right-hand side of equation becomes the production efficiency multiplied by the per capita capital to the power of theta, then where does the L goes, which is the total labor input? Well, remember that we assume that the size of the population equal to the total labor input. So then the LT divided by the NT power to the 1 minus theta will be cancelled out and then becomes 1. So then we can successfully convert the equation into the second new equation. Let's skip the third equation for the time being because it's more complicated, so I'll discuss it later. But for the first equation, that is the total output equal to the total consumption plus the total investment. So how to convert this equation that expressed in aggregated term into the per capita term? Well, similar to the practice of the first equation and the second equation, we can divide both sides of the equation by NT, and then we will be able to successfully convert it both sides of the equation into the new expression, that is the per capita output equal to the per capita consumption plus the per capita investment. Now let's turn to the third equation. As you can see in here, if we adopt the principle we used earlier for converting the equation expressed in terms of aggregate into per capita, then we need to divide both sides of the equation by either NT or NT plus 1. However, if we divide the equation by NT plus 1 for the both sides, then we are going to have KT plus 1 over NT plus 1, and indeed we will be able to convert the aggregated capital stock next period into the capital stock per capita next period. However, for the right hand side, the KT over KT plus 1 doesn't equal KT, IT over NT plus 1 doesn't equal IT. So then the other way we can do is that we say, hey, how about divide both sides of the equation by NT? If we do that, then the left-hand side of the equation is the KT plus 1 over NT, and it doesn't equal KT plus 1. But for the right-hand side, we can successfully convert the capital stock in aggregate into the capital stock per capita and the investment per capita. Therefore, let's see if there is any way we can resolve the issue for KT plus 1 over NT. It turned out that if we look at KT plus 1 over NT, we know that KT plus 1 over NT does not have any economic meaning, but if we separate the KT plus 1 and NT out, then we know that the right couple for KT plus 1 is NT plus 1. Given that we divide the equation by NT plus 1, as long as we multiply it back, then the equation will be kept. So then in here we will notice that now we will be able to have a meaningful expression, that is the KT plus 1 over NT now equals KT plus 1 over NT plus 1, which equals the KT plus 1 in lowercase, which means it is the capital stock per capita. So now it is a meaningful term, and then multiply the NT plus 1 over NT. Then what does NT plus 1 over NT means? It means 1 plus N. The N here is the population growth rate, because the ratio of the population next period over the population this period becomes 1 plus the population growth rate. Okay, so in here you will notice that if we divide both sides of equation 3 by NT, and then the left-hand side of equation will becomes the 1 plus N multiplied by the capital stock per capita next period. The right-hand side of the equation equals 1 minus delta multiplied by the capital stock per capita at time t plus the investment at time t in per capita term. And so we successfully converted the third equation that expressed in terms of the aggregated variable into an equation that expressed in terms of per capita variable. Now let's look at how to solve the system of equations we set up for Solow model above. So let's recall the four equations that we have right now. We have the CT, which is the consumption per capita equal to a portion of the income YT. And then the YT can be produced using the capital stock per capita augmented by the production efficiency. The third equation tells us the accumulation of the capital follows the law of motion. The fourth equation tells us whatever amount of goods that is produced need to be either consumed or invested. So then when solving this system of equations, I want to argue that we can simply focus on the capital stock, because once we know the capital stock for each period, then we know the value of all the other variables in the same period. So let's see why that is the case. So now let's look at the first equation. We know that if we know the variable value for the output, then we will be able to come up with the variable value for the consumption. From the second equation, we know that as long as we know the variable value for the capital stock at time t, then we know the output per capita at time t. So then if we combine the first and the second equation, we know that once we know k, we know y, and then we know c. Moreover, from the third equation, we know when we have the capital stock at this period, once we know the investment this period, and then we know the capital stock next period. Then from the fourth equation, we know that once we know the y and the c, which is the output and the consumption, then we know what is the amount of the investment. In other words, if we combine the third and the fourth equation, we will be able to come up with the capital stock next period. Because from the fourth equation, we know the I, and then we can plug the I into the third equation, and then we know the KT plus 1. So to wrap up what I say in here, we say that we can argue that when we are trying to solve this system of equation for the Solow model, we can simply focus on the capital stock level. Once the capital stock level for each period is determined, then all the other variable value can be determined. Because from the first equation and the second equation, once we know the k, we know the y and c. And then from the fourth equation, given that we know y and c, we know the I. From the third equation, we know once we know the I and the k, then we know the kt plus 1. So then once we know kt plus 1, then we can plug in into the first and the second equation again. We are going to have yt plus 1 and ct plus 1. Then again, based on the fourth equation, we will be able to get the it plus 1, and then when we plug this value into the third equation, and then we will be able to get kt plus 2. Therefore, in this route, we know that once we know the initial k, which is kt, then we can determine the value of yt, ct, and it, and then we also can determine the kt plus 1. And then once kt plus 1 is determined, we also know the value for the yt plus 1, ct plus 1, and it plus 1. And then we also know the kt plus 2. In other words, once we know the first period capital stock, we also know the future capital stock level. So then once we know the k, the entire transition path for the economy is determined. So once we know the k, we know the value for all the other variables for all the time afterwards. So that's how we solve the system equation for the Solow model. We focus on the k. Because of that, we want to focus on a special type of the k, which is called the capital stock in the steady state. You can think about this steady state is that once we are there, we are going to stay there forever. And then so in the model concept, we think about this steady state. It's the state that the economy is going to achieve in the long run. So then to determine the capital stock in the steady state, then we need to look at the third equation, because this is the only equation in the system of equation that characterizes about the variables across time. So given that the economy is in a steady state, so the narrowest definition for the steady state is that the K will stay there forever. Therefore, we assume that if the economy attains the steady state, then KT plus 1 need to be equal KT. So then we can plug it in and then rearrange the equation. And then we are going to have this new equation. That is, n plus delta multiplied by KT need to be equal IT. And I have a name for this condition, which is called the steady state condition. So now when we want to solve for the Solow model, based on the Solow diagram and based on the equations, we need to plug this steady state condition in, and then we will be able to solve for the steady state for the economy. And then we will be able to know how does the economy look like in the long run.